Good morning. We are ready to move on now into Chapter 35. And Chapter 35 is a continuation of what we were doing in Chapter 34, which is looking at interference effects with light. So in Chapter 34, we had introduced kind of the quantum physics properties of light. We said light consists of photons, and that the photons are not following one definite path, but photons can follow many different paths at the same time, and that there's an interference effect that takes place between those different paths. So in Chapter 35, we are going to be looking at more than what the title is, more than diffraction and polarization. We're going to look at diffraction, and also we're going to go back and look at some multiple slit interference effects. Polarization is kind of its own topic, so when we get to polarization, we'll talk about that, but polarization is not an interference effect. It's an important property of light and other particles, but it didn't have a chapter of its own, so that kind of got stuffed in with interference effects. Anyway, let's get started and see what this chapter is going to be about. There's a list of topics within the chapter. Again, I'm going to run through those pretty quickly and start talking a little bit about diffraction. Now, diffraction effects show up when we take a close look at light passing around different objects. What we find is that the shadows that are cast, they don't have a distinct border to them. And in fact, as you get closer and closer to these edges, as you look at the pattern around these edges, there's actually alternating bright and darker regions. So kind of the same thing we saw with the two-slit effect. And sure enough, it's an interference effect that's taking place. Now this is kind of crazy. I don't know if you've ever done this, but if you take your finger and a thumb and you create one, a narrow path between your finger and thumb, and then you close it down and you look through it, at some point you start to see an interference pattern. So as the width between that gets really narrow, try that sometime. You're just sitting around in a room looking at something, and as you get closer and closer, at some point you see alternating bands of bright and dark regions. And it's an interference effect when light passes through any kind of a narrow opening, or as it passes around any kind of an object where part of the light is removed, then you end up with these interference effects. So that's what's happening here. This is a picture of a diffraction effect or an interference effect behind a disc, a very circular disc. And if you can create a circular disc that's very uniform, you actually get a bright spot at the center at the back, because the light going around the disc at the very back reinforces at the very center location. Here is a razor blade where they've shown this. Now this is more of a traditional sort of a single slit interference pattern, and that's what we're actually going to be taking a look at in this chapter. We're going to be taking a look at some of the simplest sorts of interference effects. So here's some more. These are single slit interference. There's not two slits here now. It's a single slit that's creating this interference pattern. Light is passing through a single slit. There is what we call a central maximum. This was done with two different wavelengths of light, something in the green, something in the red. So there's what's called a central maximum, and then from that central maximum, we count back. There's an m equals 0 at the middle. With two-slit interference, the integer values of m showed up at the peaks, but in diffraction, when there's only one slit, the m values are going to be 1, 2, 3. The integer m values are going to end up at the 0 intensity locations, and we'll derive all this, so we'll get to see how this works. But that's a really nice picture of a diffraction effect from just a single slit. So here is a diagram of what we just took a look at. And what it's saying is that it's a single slit, diffraction pattern, and the minima, which are predicted to be zeros, occur at integer values of m, where the formula we're working from is a sine theta equals m lambda. Now, in chapter 34, again, we're going to draw a lot of comparisons here because the good news is if you worked through chapter 34 and you have a pretty good understanding of how that works, this is going to be pretty analogous. Okay, and then once you've gone through both chapters, you can kind of switch back and forth to keep reminding yourself of which properties there are from the multiple slit effect versus the diffraction effect. So what we're looking at is called a diffraction effect. A in our formula is the width of the slit. So if I have one slit, I still have many paths that the light can follow. Because if I have one slit, well, there's a finite width. The light could be following any of those paths that follow between that slit. So in the intensity pattern, there's a central maximum. We saw that. And then there are what are called fringes out to the side. So if we just flip back and forth between these two, that central maximum, see how much brighter that is? It's like 90–95% of the light ends up going into that central maximum, and then there are these fringes out to the side. Now, this is the formula that keeps track of at what angle, at what location on a screen or what angular location are the m values, the different m values based on the wavelength and the width of the slit. And then this is the intensity pattern, or the intensity formula. And the intensity formula is written in terms of m, pi, same as what we saw with two-slit interference. It's a little more complicated, though. There's more stuff going on, and we'll derive both of these formulas and see why a single slit would create an interference pattern like the one we're looking at. So here's a picture or here's a series of diagrams of a single slit. So here is the barrier. The light's coming through. Each photon has many different paths it could be following. So we have to consider the possibility of the photon following each and every one of those paths. And then we move over to where the screen is located. And when we get to where a screen is located, we ask, what are the path length differences? If there are path length differences, those will lead to difference in phase, and those will lead to interference effects. Now, a couple things I should point out right now. In my notes, I am going to use little a for the width of the slit. That's a common, that's very common in a lot of textbooks and a lot of notation that we use for the slit widths. Our textbook in the most recent edition has switched over to capital D. So if you see a capital D for the slit width, that's the same thing. That's interchangeable with the little a. We'll see that I'm reserving big D for diameter. We're going to run into some circular situations later in the chapter where we need to use big D for a diameter. In any case, this is the slit width. And if we look straight ahead at the screen, all those paths are going to follow essentially the same distance to reach a point right straight in front. And that means that they're all going to be in phase with each other, and that's going to give us a bright, constructive point. Now, why is it when we get to m equals 1 that instead of having a bright region, we have a dark region? You go, well, diffraction really is different than a series of slits, because diffraction means that you've got this continuously varying phase between each one of the possible paths. So what we have to consider is, well, there's a path here and here and here, and each path is just a little different in phase than the path right next to it. So we have to take into account all of those infinitesimal path length differences that occur from one path to the next. One way to think about this is if I take, once I move this to an angle, one of these paths will be the shortest path to the screen, and one of them will be the longest path. And in this case, what they've shown is for m equals 1, this most extreme, longest path is going to be longer by one wavelength. That's why it's m equals 1. So one wavelength difference, and one wavelength difference means that this path will be in phase with this path over here, kind of like what we saw with the two slit example. The difference now is that it's not just these two paths, it's all the intermediate paths also. And what we can show is that if I take this path and compare it with the one in the middle, or this path and compare it with the one in the middle, those are a half cycle out of phase with each other. And if, as we move along the width, we can show that the pairings that occur for each one of those paths will consistently cancel each other out. We'll see this in more detail when we do a phasor diagram, but the key feature now is to remember we have to keep track of a continuously varying phase difference, and that leads to no intensity. That leads to complete destructive interference in this case. All right, what happens when we get to m is equal to 3/2? So in this case, this longest one is longer by a wavelength and a half. It actually turns out when we add all these things together, we get a bright region. Now, it's not as bright as the central maximum. This is something going on in one of the fringes. And then when we get to this path here, now we're at 2 full wavelengths. And what they're trying to show with this diagram is anytime you hit an integer number of cycles difference across the entire width, it's going to cancel out completely. Okay. So we'll get a chance to come back and revisit this and see how this is working. Let's look at an example. So here we have an example of single slit diffraction. And what we're taking a look at here is, in particular, the central maximum. Now the central maximum, again, that's like 95% of the light lands in the central maximum. Only a few percent ends up out in the fringe areas. Here is the light coming in. Each individual photon is following many different paths. Now, many of those paths end up running into the barrier. And if there's a high probability of the photon being blocked by the barrier. It gets absorbed by the barrier. But there's some finite possibility that the photons end up passing through the slit. And for those photons that don't get absorbed by the barrier, that do pass through the slit, there's this range of directions that they could end up traveling. So we have to take all of these into account. Now, if we look at a point straight ahead on the screen, that's what we're going to have our highest probability of the photon ending up. So that's what the central maximum looks like. Now, what they're suggesting to us here is the m equals 1. Here is m equals 0. Here is m equals 1 on the other side. They want us to go in and calculate x. They want us to calculate a distance on the screen as to how wide that interference pattern is. So the light we're going to use is 750 nanometers. Now, often we've been saying that the visible light spectrum only goes out to about 700 nanometers, but we can actually, our eyes can pick up farther out beyond 700 nanometers. So here they're suggesting that human vision goes all the way out to 750 nanometers. This would be at the really, really red end of the spectrum. And then it passes through a slit. The slit is said to be 1/1000th of a millimeter wide. So this is a really narrow slit. We can't see thousandths of millimeters. those are like microns. Those are the size of individual cells. So anyway, those are all the numbers. Here's the setup on the problem. Now I did go ahead and use their convention of using big D on this problem, and so my formula here says big D sine theta is equal to m lambda, and I wanted to get the D and the lambda stuff written down. My wavelength, they said, was 750 nanometers, so that's, you know, red light, and the distance, the width of the slit, I converted that also into nanometers, and that works out to be about 1,000 nanometers. It's a really narrow slit, so 1,000 nanometers is very, very narrow. It's not much bigger than the wavelength of the light that's passing through. And then the distance of the screen is 20 centimeters. So first of all, I went after the angle. Where are the m equals 1 locations going to end up? Because the m equals 1 will tell me the limit of where that central maximum ends. So, and if I guess we could do this. Let me flip back a few slides here. That wasn't so far back. So this is what we're trying to do. There's m equals 1. There's m equals 1. We actually have a lab where we take a look at this. So, if, you know, the lab number 3, I think it is light interference, and we have some. If you watch that lab video, you will see these interference patterns being set up in the lab room, and then we go in and do measurements using rulers with these. So that's what we're looking at. And I was able to go in and solve for the angle where m is equal to 1, and that worked out to be 48.6 degrees. So we've determined what these angles are. Now what we want to do is find the x values. So we can do a little trigonometry here. If I do the tangent of theta, the tangent of theta will be x divided by L. And so that says x equals L tan theta. I can plug all the numbers in. It says that the distance out to one of those edges of the central maximum is 22.7 centimeters. That says the distance all the way across the central maximum is 45.4, I guess. 45.4 centimeters is the width of the entire central maximum. Okay, those are you know, typical kind of questions that come up in this chapter. Now they're asking us, you know, here's a slit. Now it's not especially narrow this way. They're asking what the interference pattern might look like, what kind of a diffraction pattern I would get on a screen if I sent it through a slit like this. Now it is narrower in this direction, so we do expect that we would get an interference pattern along this direction, but we'll also get an interference pattern this way. So what happens is we'll end up with kind of a rectangular, we'll end up with some kind of a rectangular central maximum, and then it will be surrounded by these fringes that wrap around that rectangle. So that's what we're guessing here as far as what the interference pattern would look like. Here we are back to you know, kind of our derivation of as to how did we get our formula, our d sine theta equals m lambda. And so if the screen's off in that direction, then we imagine, you know, there's an infinite number of paths here, and each one of those paths has an amplitude of, it's infinitesimal, it's dA. So we got a little bit of amplitude here, a little bit here, and a little bit here. Each one of these has a little amplitude dA. If we add all the dAs together, we get the total amplitude A. Now the book is using DE and E, but as we talked about in chapter 34, those get kind of used interchangeably in the textbook. So be prepared for either one of those notations. Now the extra path length difference here is going to be d sine theta, and that can be derived the same way we did that back in chapter 34. if you remember, if this is the width, d here, and then the distance that this wavefront is shifted over is, that's shifted over by an angle theta, and so this side, this is the hypotenuse, this side of my right triangle is d sine theta, and that's what we set equal to some number of wavelengths as a way to go in and derive our formula. So that formula is going to relate what is the m value as I move across the screen. And the m value is going to give us an idea of what the intensity is. So here's my own drawing of that. Here is the width, here is the angle, and again, you can think of this as an infinite number of infinitesimal widths. So each one of those little tiny portions of the width is contributing a little bit of electric field or a little bit of amplitude for us. And this is the formula that we end up with. This becomes d sine theta. M is the number of wavelengths difference, the total number of wavelengths difference across the entire width. So it's the difference between one edge of the width and the other. Now, if you guys remember these phasor diagrams from chapter 34, here's some more examples using the phasor diagrams. And let's see, we were talking about each of those paths, and this is in terms of their notation with the electric field. So let me work in those terms. So there's there's a whole bunch of paths, many paths. And if I'm looking straight ahead at the screen at an angle of 0 at the center of the screen, then all of those little infinitesimal paths are all exactly in phase with each other. So what that gives us is this. If I add all of these little paths, now they're calling them delta E naught, but I'm going to call them infinitesimal. So I'm going to call them dE or dA, a little bit of amplitude. If I add all of these little amplitudes together, what I end up with is what they're calling E naught. Now, that's when I'm looking straight ahead at the screen. What happens if I'm looking a little bit off to the side? Now, in this picture over here, what we've got is we're looking a little bit off to the side. Each one of those successive paths is a little bit longer than the one before it. And that says that each path is going to be a little bit out of phase compared with the one before that. Now, if I take a whole series of little short amplitudes or short electric field quantities and angle them by a small angle, that path's going to be a circular arc. So when I add all of these continuously varying phases of all these infinitesimal segments, that's going to produce a circular path. So that's part of a circle. Right? Now the length along the curved path is still going to be the same as the length of all of these infinitesimal amplitudes right here. So if we're going to call this E naught, which the textbook is doing, then this continues to be E naught when I move along the circular path. But now I need something that tells me what the interference effect is, because over here E naught was the length of all these little individual pieces. E naught was also the net effect once we had taken the interference into account. In that second picture off to the right, that's going to change. So now, once I've taken all of the interference into account, the overall amplitude is going to be this straight line. Or if it's a circular arc, I think you call those chords, something like that. So that's kind of interesting. What's happening is the effective electric field, or the electric field amplitude, the net effect, the total effect once I take interference into account, is less than all of the individual pieces added together. Okay, I'm going to start getting a bit of a destructive interference effect due to the phase differences. Now, this is actually at n equals 1/6. And the way we can tell that is if I take the first one here, the first path, and then I compare it with the phase of the final path, what this is showing us is there's an angle here that's about 60 degrees. I think I may have made up that 1/6. I should have gotten a protractor out and measured it exactly, but I think that is it. So this is 1/6 of a cycle difference by the time I get to here. Okay, so that's what the A total or the electric field for that angle would look like. What happens if I continue to look at a larger and larger angle along the screen compared with the center direction? At some point, I'm going to reach a point where the phase differences are large enough that if I look at one edge of the width and the other edge of the width, they're going to be out of phase by one exact wavelength. Okay. Now I'm hoping with these phasor diagrams, if you stop and think about what they're representing and kind of stare at them long enough, what this is saying is if the ones at the edge are exactly one cycle out of phase with each other, that means that between those two paths, that continuous region where the phase is changing continuously, that's going to exactly cancel out because I have every possible intermediate phase there, and the effect of all of those phase differences is to completely cancel out. That's why the integer values of M give us zero intensity, because we're getting complete cancellation of all the possible paths. Okay, so does that make sense? Kind of. Again, it's something. It's a powerful technique working with these phase differences, and so it's worth putting a little time in. Taking a look at the slides we have here in the lecture, and then taking a look in the textbook too. They're going to have kind of the same stuff explained there. If I continue to look farther along the screen, they've picked out one other location here. This would be n equals 3/2. And that would say that if I look at my first path and I look at the phase difference, it's 1.5 complete cycles. So that's a value. That would be a value of 3/2. And notice that as we look farther and farther across the screen, we never reach a point that looks like this again. With just two slits, every time we got to an integer value, things lined up again. We had a maximum, we had an intensity peak. But the diffraction effect is as you move farther and farther away from the center, your intensity is going to drop off. Now, again, I keep referring back to this picture because it's so handy to refer back to. So that's what's happening. So here we have n is equal to 0, m is equal to 1, where everything canceled out. Well, then we go through on our phasor diagram between n equals 1 and n equals 2, we go through a region where it's not complete cancellation, but it's mostly getting canceled out. And then when we go from 2 to 3, the effect is decreased even more. So each one of these peaks is getting less and less. Each one of these fringes has an intensity that's dropping off. And that's because the phasing effect of the different paths is forming a tighter and tighter spiral, or a circular path. Okay. Now we're going to come back from these diagrams, use some of these diagrams to derive the intensity formula. So let's do that. This is a good diagram. Here's another one that they're going to use. So what it's saying is that if I add up all the amplitude coming into the slit, I can put that along here. They're calling that electric field reference, or E naught. I'm going to call that A, as in the amplitude for that particular opening. And then they're going to say that once I've included interference effects, what's the overall electric field reaching the screen at that point? They're calling that the electric field or the amplitude as a function of angle. I'm just going to call it A total. So I'm going to say that once we have included the effect from all of the paths and their interference effect, I'm going to be left with an A total, and the A total is going to vary across the screen. Straight ahead, the A total is going to be really large. When we get to integer values, the A total is going to drop off to 0. Now, they introduced this phase angle beta as the angle between the first path and the final path. And if we do a little geometry, what we can show is if this is beta, then this is the supplement of beta. And if this is the supplement of beta, if we take a look at this path, then this angle here is going to be the supplement of the supplement. This is going to be beta up here. And so if this angle here is beta, I'm going to draw a perpendicular bisector, or they're going to draw it, and put it through my diagram. And that perpendicular bisector is really handy because what it does for us is it creates a right triangle here, and there's another right triangle here. But there's a right triangle here, and this right triangle has an angle of beta over 2. Now, the length along here is 1/2 of E theta, or 1/2 of A total. When I look at the circular arc, remember this is a circular arc, I can also take the circular arc and run these two lines back up to the apex and say that this angle right here is equal to 1/2 E naught divided through by R. Okay, so we have another diagram here to look at, and you guys can flip back and forth to see how this works. Now I have changed over and written this in terms of a whole series of little tiny dAs, and once I add all of those dAs together, I will get the total amplitude of light coming into that width. So the light coming in has a total amount of amplitude, and then that amplitude we can divide up into a whole series of dAs, and then we can take into account their interference effect. And once we've taken the interference effect into account, what we'll end up with is an A total for that particular location on the screen. Right. And then we're going to use the geometry that we talked about. What we can do, I'm going to start with sine of 1/2 beta is opposite over hypotenuse. That would be 1/2 of A total over R. For the arc length, the angle in radians of 1/2 beta is equal to 1/2 of A, which would take us out to here, divided through by R. Now I can take these two formulas and divide them by each other. So if I take the right side and if I divide the two right sides through, the 1/2s cancel, the little r's cancel, and I'm left with A total over A. When I look at the other side, what I have is sine 1/2 beta over 1 beta. Now, beta is a phase angle, and phase angles can be converted over into cycles. So this is the conversion between working in terms of phase angles and working in terms of cycles, and it's a factor of 2 pi radians per cycle. So you can also write this as sine m pi over m pi. Now to find out how much intensity we're getting, what we do is we square the A total, and then we say that the intensity is proportional. So as a proportionality constant, we use I naught, and the important part of the formula is to square sine squared m pi over m pi squared. So that's where our intensity formula is coming from. Now our intensity formula that I'm using is written in terms of m, and it could have been written in terms of beta. So you'll see this written as beta, or you'll see it written in terms of m pi. Okay, so this problem, example 35.3, is saying, well, okay, let's take a look at one of these diffraction intensity patterns. It's m equals 0 right in the middle, and then 1, and then, I didn't scale this very well, 1 and then 2 and then 3, 1, 2, 3 in the other direction. Here is the intensity formula. What happens in the limit as we approach m equals 0? Okay, and what you would think is, well, what is the intensity right at the center? I can put an m equals 0 in here. That becomes the sine of 0, which makes it look like 0, except the denominators go into 0 at the very same time. So if m goes to 0, I can't just plug the numbers in. I have to find out in the limit, as m does approach 0, what happens to the numerator, what happens to the denominator. Now, the approximation for the sine of an angle, or the sine of any variable, is that as that variable goes to 0, the sine of x becomes x. If you plot the sine function, and then you plot the function, just a linear function x, that is the slope, initially, of the sine function as you're looking at the origin. So in any case, I'm guessing you've seen this in your calculus classes. You may have forgotten about it. But there are these approximations. If you expand the function sine of theta, the first term in that expansion is theta. And so what that's telling us is that this expression, as m goes to 0, all of this expression becomes 1. And remember, this was a proportionality constant that we introduced. And it says that the intensity at the center, we're going to designate that as being I naught. Okay, that's a lot to take in. I know this is kind of a different approach, and it's kind of like, wait, who made up all these rules? And I guess nature did. So this seems to be the way that nature is working. So the intensity right at the center is defined to be I naught, and that's it. So that's what happens right at the center. Now, as we look away from the center, where are these other peaks going to show up? Our phasor diagrams told us that at the integer values of m, the intensity is 0, but where are these smaller peaks and how large are they? So to solve that problem, what we can do is we can use a little calculus. What we can do is we can take this function and take a derivative of that function and find out where the slope is 0. Because wherever the slope is 0, that's going to allow us to find the minimum and maximum, or the maximum values of that function. So what we can do is this. Instead of taking this function, which looks a little complicated, I could replace this with sine of u over u. So I did that function instead, and it was a good chance to use the quotient rule for taking derivatives. Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And what I ended up with was this function. And I set that equal to 0, and I solved for it, and look, its tangent of u is equal to u. Now this variable substitution, u is taking the place of m pi, and so I can plug that in. So what we've got now is that tangent of m pi minus m pi is equal to 0. So this is the problem I'm trying to solve. Now it turns out this is what's called a transcendental equation. I'm not sure you remember this from your math classes, but there's many equations that cannot be solved algebraically. There's no way to manipulate this using algebra to solve for the values of m. So what you have to do instead is you have to find another technique to solve them, something like successive approximations. So I programmed my calculator My calculator, first of all, it's programmable, and then you can take the function that you've programmed into it, and there's a function called solve, and it will find the solutions for you through successive approximation. So I did that, and what I found was that this solution, this equation, has solutions for m is equal to 1.430, m is equal to 2.4593. So what you can see is that the peaks, these are the m values of the peaks. So the peaks are not landing at 1.5. The peak right here that I've drawn is actually at 1.430. You go, well, why aren't the peaks landing at the half integers? Well, let's take a look at the function. When m is a half integer, the numerator becomes 1. So the numerator is very happy at a half integer. But notice there's also a denominator going on here. And the denominator, as m increases, reduces the intensity. So it's kind of a trade-off here between what's happening with the oscillations in the numerator and this linearly increasing denominator. And so, you know, the solution turns out to be at 1.43. This peak right here is not at 2.5, it's at 2.459. Now, as I look at these other fringes, what I'm finding is that the peaks of those fringes are getting closer and closer, I think, to being located at a half integer value, but that process isn't happening super fast. Okay, so sometimes we approximate this as 1.5, 2.5, but we don't have to. You could write these down in your notes. You're welcome to hang on to those first 4 that we've solved, and use those when you're doing homework problems, or use those when you're doing midterm exams. Use those. I don't expect you to drive these, but you're welcome to go ahead and use them. Once we've determined what the m values are of the locations that give us the locations for these peaks, then I can plug that back into my intensity formula. So I can plug these now back into the intensity formula, and from that I can determine what the relative intensity is. So I'm going to take this intensity formula, and I'm actually going to think of this as I over I naught. So I'm going to divide the I naught through and bring it to the other side. I'm really solving this portion right here. Now I know this function goes to 1 right at the center, so that's my comparison here is with 1. And when I solve that for the first fringe, that brightest part of the first fringe, I get 0.04719. And that tells me that the intensity of that first fringe, peak, is about 4.7% of the intensity at the center of the central maximum. So that's only at about 4%. So see, this should be 20 times higher than this. This is at 4.7. What about this peak here? This peak is only at 1.6%, and the next peak over 0.8%, and then 0.5. So you can see the prediction here. Think about those phasor diagrams and what's going on with the all of the paths leading to those locations. What's going to happen is these intensities are going to drop off pretty quickly. Okay. All right, any questions on that? That seems to make sense. Okay, it's a good thing to spend some time with. So again, those numbers that we just came up with, if I go back to this single slit diffraction example that we looked at way back here, it's predicting, once we've got our intensity formulas, how bright is it here, or how bright is it here compared with here? How bright is it here? How bright is it here? We calculated those first 4. This was like 4.7% as bright. This was what, 1.6? Something like that. 0.8%, 0.5%. So you can see how those intensities at those peaks are dropping off with distance. Okay. I think we're getting pretty close to the end time for our, we've got a few minutes left here, so let's get this topic started and we'll probably pick up here on the next lecture and overlap a little bit. But what we're going to do now is, now that we've got this diffraction thing figured out, I'm thinking, oh my gosh, you know, last chapter, chapter 34, when we were looking at two-slit experiments, you guys remember that, those slits had a finite width to them. Back in chapter 34, we were using an approximation that assumed that the widths were infinitely narrow. They were infinitesimal in size. Well, that's not reality. Reality is that the widths do have, the slits have some width to them. So what we got to do is come back and take both of those effects into account. So what's that going to look like? And it's going to look like this. And so what's happening here is, let's see, this is the diffraction that we just solved for. That's a single slit creating a diffraction effect. Well, when we go to two slits, the diffraction effect will still be present. Each slit, the width of each slit will be creating a diffraction effect. So if we have two slits, then I'm going to have this two-slit effect. Now remember, this was the two-slit effect that we saw in chapter 34. And if we used a circular screen and assumed that the slits were infinitely narrow, then we got a series of equal intensity interference peaks. Now what we're going to do is we're going to take the diffraction effect and combine that with the two-slit effect and say this is what the interference effects are really going to look like. What's going to happen is, if I have a two-slit setup, I'm going to have the two-slit effect taking place, but that's going to all be moderated by this diffraction effect. So the peaks aren't going to be the same intensity. The intensity of the peaks are going to drop off with distance. And there it is. So this just sends chills down your spine, right? Thinking, oh, that's amazing. So we've got light, this is light, going through a two-slit setup. And there's a certain distance between the slits, and then each slit has a certain width. And what you can see, and this is kind of a side-by-side rough comparison, here is the diffraction, the central maximum of the diffraction effect. Here is m equals 0 for the diffraction. If I think of the two-slit effect, well, here's m equals 0, n equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It looks like the 12th interference peak from two-slit, the 12th two-slit peak, is being squashed by the diffraction effect. Okay, so what we want to do is combine those two effects together so that we can make a prediction mathematically as to what that intensity looks like. And so that's what they've done here. What they've done is they've said the amplitude, the electric field reaching the screen, has, well, here's the two-slit effect. So this is kind of interesting. They took the two-slit effect, the 2 and the cosine, and put those on the outside, and then they put the diffraction effect down the middle, but that's it. In the textbook's notation, where they're using phase angles, so they're using delta and beta as phase angles, and they're using E naught as the amplitude for each slit. Now, what I've been doing, for better or worse, is I have been, oh, I did the same thing. I apologize. Here is the effect from two slits. 2a cosine m pi. Here is the effect from diffraction. Now, I can't use m for both of these. I can't use the same m. They got to be two different m's, or I've got to define a different variable. So I used n. So when I'm looking at the interference effect for two slits, including two slit effects and diffraction, I am going to switch over and use n. Now n's not the index of refraction. It's just a different variable keeping track of the number of cycles. Okay, so we'll come back. I'm gonna stop there. I think we're through for the it's time to take a break. So let's take our break for the day, and then when we come back, I think we are here. So we'll come back to here after the break.